and let's roll. So today, we're going to go into lesson 7. This is effectively supposed to be the last class, but you know what? People want to learn operator overloading. So we're going to have an extra class dedicated to operator overloading next week. Make sure to be there if you want to know about operator overloading. It's a really cool C++ feature. You won't know about it in most other languages because a lot of other languages don't support it for various reasons. Some going to the fact that it can be very confusing to look at, others just because they didn't want to implement it. Java is one of those languages that decided not to implement it because they thought it was too confusing. And it's reasonable, which is why it's probably important to know how it works. So if you're looking at it, you'll see what's going on. Fine. Anyway, so let's talk about smart pointers, auto, and references. These are strong C++ features that make a huge differentiation between what is C and what is C++. C does not have any of these things. Actually, the latest version of C might have auto, but let's pretend I didn't say that. C doesn't have any of these things, and many other languages don't have the auto or explicit references. So let's talk about what these things are. So first, a quick recap. Talk about smart pointers real quick. Let's go into unique versus shared. All right, I'm sure everyone can tell me what this is right now, but we'll go over it. So, what is unique? Hey, I was doing the thing. You can only have one unique pointer per object. There are no exceptions to this rule, pun intended. If you have more than one unique pointer pointing to an object, what's going to happen is the compiler is going to get very angry at you, and it's just going to say, no, you cannot do it. The compile time errors, and then from there, too bad, it's not going to work. This is a very easy mistake to make, and we'll show you why. Not yet, soon. All right. Following that, we also have the shared pointer. Shared pointers make it so you can have as many shared pointers to an object as desired. This makes managing shared pointers much easier, at least in terms of what you're going to point to and making sure you don't have compile time errors. However, it does bring its own set of problems. Unique pointers. One more. Can't be two unique pointers to an object. Sure, no exceptions. And this also includes functions, okay? It's very important to remember. I believe that's, yes. So, because C++ is copy by value, and it's not copy by reference, what happens if we pass something into a function that has a unique pointer is that the compiler is going to get mad. And why is that? Well, no, stop. And that's because what we do when we pass a unique pointer into a function as an argument, we're now copying that unique pointer and putting it in another function. By doing so, now we have two unique pointers to a single object. And that gives us an issue. We can't have that because now we've unintentionally made two pointers and the unique pointer doesn't like it. So how do we fix that? C++ 11 and C++ brings move. Move allows you to move delete one pointer's old references to an object and then assign it to another pointer. And this is essential if you're passing unique pointers into functions and is effectively required if you want to use unique pointers in functions. All right. What it does is it creates a new unique pointer with the type of whatever and points to the object in the function. All right. I think that's the end of that slide. So let's actually get some example here. And I'm going to kill this for a moment. And let's get a terminal over here. And cd code. Let's make it big. Keep in mind I'm working off of this monitor right here. And inheritance. Now, what is this? No. Now, if you remember this that I was going over a while ago, I used this example to talk about how inheritance worked. So let me bring up this real quick. So GCO, I'm going to check out our raw pointers branch. I'm going to go into our source folder and bring up main. It's a very tiny main. Here we go. And if you remember, this was the one where we talked about the object-oriented toaster. We had all sorts of foods right here. bananas, bread, we had eggs, we had pancakes. And what we did was we passed it into a vector of foods, pushed each one back by address, and then we were able to access it using this vector of food. Cool. But what happens is now we're using raw pointers right now. And the issue with raw pointers is that if we have two raw pointers accessing something and our object just happens to disappear, we're going to have a seg fault. We don't want that. We don't want our code to be exception safe, and we want to make sure it's crisp, clean, and easy to read. So let's fix that. Or rather, let's just try and make some unique pointers and add them in right now. So in order to add any type of smart pointers, we need to include the memory header. So we're going to do include and memory. Cool. That's all we need. As an aside, it's also required that you compile using C++11. Older versions of C++ do not support these smart pointers. You're limited to use auto pointer in older versions of C++, which is absolutely terrible, and in fact it doesn't work in later versions of C++. So we're not even going to go over it. Imagine you took bad things from unique pointers, and bad things from shared pointers, and then some random bad things that were just like floating around in people's heads. Just put it into an object. This would be auto pointer. So pretend that doesn't exist. All right. So let's go about making some unique pointers. So in order to do this, first we need to make. First we can do this: std : unique and pointer. And then we'll make it type, we'll say banana, or bananas. Make some pointers to our bananas. And we'll call this banana pointer. And there's an issue with this. We can't just pass a reference in here. So what we need to do is instantiate it as is right now. So we'll do new banana. And we're good to go. Comment this out, and this is our main source of banana now, this banana pointer. Just like we can do with vectors, we can also get rid of the std : and we're actually going to do that just so I don't have to type that out every single time. So using standard and then unique pointer. Beautiful. Something that's very important. Oh yes.
What does new do again?
New. So when you instantiate an object, there are two places it can be instantiated. Where did my marker go? Is it on my marker? Is it gone? My marker's gone. I don't need a marker.
Does it make it on the heap or something?
Makes it on the heap, yeah. So instead of instantiating on the stack, it instantiates on the heap. That's really all there is to it. You need to be careful of memory management then, because now it's dynamically allocated. But other than that, there isn't too much. It's also accessed via pointer. So we've made a pointer to said object, and now we're referencing it. Great. But before we do anything else, we also need to make it so our vector takes in unique pointers. So let's modify our vector so it can take in unique pointers. So unique pointer, and this will be of type food. All right, nothing wrong yet. We'll only focus on bananas for now. So we'll put all the stuff away and pretend it doesn't exist. Now what we need to do is put our banana inside this function. And I'll do so by just typing in banana pointer. Seems good? Maybe? Okay. And finally, one last thing. We're going to modify these functions so that they take in unique pointers. So this will be unique pointer of type food. And this will be of unique pointer type food. All right, can anybody tell me what's wrong with this? All right, that's okay. Let's just run it. Maybe there's nothing wrong. Maybe I'm just lying. I'm trying to catch everyone up. Oh, whoa. Is that a hand raised? Go for it, Nick.
I don't think you can have two double carrots right next to each other.
Two double carrots?
Like you have food and carrot there.
That was a restriction in older versions of C++, but that is not an issue in C++ 11 with the GNU GCC compiler. That's actually a great thing to point out, though. That's really cool. props. It thinks,
Took me a while.
yeah, it thinks. So if you're working in other versions of C++ or older versions of C++, if you have these two things right next to each other, what happens is that it thinks it's the insertion operator, just like you would use with cin. It's not an issue with the version of C++ we're using, but know that it may happen, and you may actually notice something else in just a moment. Was that another hand raised? You noticed it too? Props.
No, I go back on what I was.
Cool. All right, let's go into our build folder, and it's time to build. So cd builds, and let's do cmake dot, and let's make this. Oh my, what happens? Who knows what happened? This is one of those crazy error messages. What could possibly have happened here? I don't even know. Well, there are a couple errors. One unintended. Let's actually fix that real quick. Let's recompile it. And we'll still get another wacky error. So, what's happened? Bananas. Me and my names. Here we go. And what's happened is that we have a real error right here. We've inadvertently made two unique pointers to an object. Here, we made a unique pointer. In here, we made another unique pointer to this object when we push back our banana pointer. Very unintended, but it happens. How do we fix that? Does anybody remember what I just talked about? Yes.
I don't catch the wholeness you're talking about. Can you point it out?
Yes. We made this banana pointer right here. It is an object of type unique pointer. When we have this vector right here, it holds unique pointers of type food. By inserting a banana pointer into our vector, oh my, did not want to copy twice. What happens is that now we've copied banana pointer into our vector. Remember, C++ works as pass by value. You're not actually passing that variable into the vector. What happens is you're passing in copy, just like what you would do with functions. Because what you're really doing is passing it into a function that's inside std : vector. And then it duplicates it and puts it there. So now we have a copy. That's no fun. Let's fix that. All right? So in order to do that, we need to do c : move. And this is going to make it so that our old unique pointer, banana pointer, is effectively worthless, and we're just going to pass it into our food vector. Cool. Everything should work great now. That's what I'm saying. Oh my. What is it not like? Building C++, unique pointer, declared here, equals delete. I'm definitely doing something still wrong. Oh. Let's get these out of the way for now. Make. Beautiful. So there is another issue, actually. But for now, we have this. It works as is. We've made our unique pointer and we pushed it back to the end of our vector. So now let's see what was wrong with this. Can anybody tell me what they think was wrong with that? And I can bring up the error again if we want. Make. And now we have our issue. Yes?
You're using another unique pointer in a function.
That's exactly what I'm doing. So how do we fix that? Yeah, we move it. So we're going to do std : move. And in fact, let's just do that for all three of these. And it'll work perfectly, right? That's what I'm saying. Move. And let's do std : move. You know, ladies and gentlemen, it's as simple as that. It doesn't get any easier, right? No. In fact, it doesn't get that much easier. And we'll go over why this happens. There are a lot of different issues with unique pointers that you need to take into account. And this is why people like shared pointers for their ease of use. And it's reasonable to say that because unique pointers are difficult to work with if you don't know what you're doing. Errors pop up all over the place because you're constantly making copies of them, or you want to constantly make copies of them. So, yes?
Why were you supposing
Supposing what?
Saying that standard move would help the situation.
Well, it does help the situation. In fact, we pass it in, and it brings us, it puts us one error down. But what happens when we go into this check preparedness function? Let's go into check preparedness, and what do we do here? We make an iterator of type I, of type food vector to pointer. And part of the error here is because we don't have the declaration correct. So let's actually fix that. But there are other errors too. Unique pointer. And let's also make this other one unique pointer as well. And we'll remake it. And the issue now is that when we make this iterator right here, note that it's also a pointer to an object inside of our vector of unique pointers. We continue to have errors because we're making more copies of said unique pointer. Each one is a unique pointer. We make a copy of it to loop through, and we're getting issues. It's very annoying, and it happens. So I'm not going to go into how we're going to fix this yet, but we will find out. Yes?
We're getting a little bit lost in the indirection. Do we have the same indirection we did before with the food pointers going on?
That's the idea. So we have this vector of unique pointers, okay?
Yeah.
What we've done is we've moved our vector of unique pointers over to this function. However, we have a for loop right here. This for loop takes a vector of food pointer. It's an iterator. It's going to iterate over our vector. And then from here, we're making another pointer right here. Well, right there, actually.
Yeah.
To a pointer inside of our function. Now we have two pointers pointing to a unique pointer, and we have an issue. Does that make some sense? Maybe? Definite maybe.
I know I is one of the pointers to the unique pointer. What is the other?
The other is the one inside the vector. So we have the vector. And here we have pointer, OX111. And that is just going to point to bananas somewhere over there. What happens when we have an iterator is now our iterator is pointing to this as well. And then we try to extract from our iterator, and what we have is now we have a pointer to what we have two pointers to what we're working with, and that's an issue.
So you're saying that iterator is holding the same address as what?
It's trying to make another pointer to our bananas, effectively. Pointer to a, it's a little convoluted, but we can't do it because just
So
note.
they both hold the address of bananas.
Yes.
So that's what pointers.
Yes, that's the idea. Well, the diagram isn't very good, but that's effectively what's happening. And since we have two,
Okay.
we can't do that.
Huh.
So, like I said, I'm not going to go into how to fix this yet, but just know that it's a little bit annoying if you don't know how to deal with it, or you didn't know it was a thing. Fine. Let's go back to our slides. Relieve ourselves of unique pointers for now, and let's zip over to shared pointers. Get back. Shared pointers. So, what's up with shared pointers? Life is pretty dang easy with shared pointers. You don't need to think too much. Your shared pointers, it's just simple with them. You make a shared pointer, you can make as many pointers to that thing as you want. Easy as that. It's beautiful. You can make endless pointers to set object without compile errors. Life is great. Nothing short of simple to write, but they're extremely heavy. They come with strong overhead. I don't even know this thing. With lots of overhead. In fact, they can be upwards of 1,000% slower than just using raw pointers. You don't get this overhead with unique pointers. What you do with shared pointers, because what happens is that you need to keep reference count and you need to keep a reference count to how many times you're holding onto that object, and it's very heavy. In fact, when you instantiate a shared pointer, you make 3 allocations in the heap. That's a lot. And to make this better, what C++ developers did was they made it so that there are multiple ways to instantiate a shared pointer. And there is a best way to do it, because why use the best way all 3 times when you can make 3 ways and then just use the best way? Doesn't make much sense to me, but it's a thing. So what we're going to do is we'll go back to our code. Wait, will we? We will. We'll go back to our code. Let's pop open terminal. Let's remove what we just did. It's wrong. Oh. And we're going to check out our shared pointer branch. And we'll go back to Sublime and refresh. And here we have already done shared pointers. Ready to go, ready to understand. You know, this is very similar to what we did with unique pointers. Make a shared pointer here. We make functions that take shared pointers of type food. And we have our main function. And here are the different ways you can go about instantiating a shared pointer. You can go about making your object beforehand using, standard constructor. And then from here, you make a shared pointer of an object equal to, or named of, whatever you want it to be. We're going to use the method call makeShared, and we have to say it's of type bananas. And then we can pass it in. Is that a question? Okay. This is, in fact, the best way to make a shared pointer. It only takes 2 allocations on the heap instead of 3. So, you should never go about just using the constructor of shared pointer like this, because that is much, much heavier. So if you're going to be using shared pointers, the right way to do it is the first way. This is, even if it looks a little bit busier or messier, making it in 2 separate lines is actually faster. And in fact, if you want to make it on 3 lines, you can even do that too. If you know that you need to make your pointer first, so we'll call it egg pointer, we can pass it a value of null pointer, and then we can make some eggs, and then we can use makeShared right here. By passing in null pointer, we don't require as many allocations because the compiler is smart enough to say null pointer means nothing, really. And so it doesn't need to do as much as it did with the second example. But, that's really all there is to it. It's a second way to do it. Beautiful. So, let's go back. Don't need to do this. So let's go over to how you would loop through one of these things. The idea is pretty similar to what we talked about before with the regular pointer. Make a vector of shared pointer, type food. We're going to use an iterator I equal to items to cooked up again, less than this, and then we're going to print out food is cooked. Let's run it. That's not what I wanted to do. And we'll go to bin, inheritance. Beautiful. Okay. So that's our shared pointers for you. It seems much easier. Just remember, there's lots of overhead that comes with these things. And why is it popping up my unique pointers thing again? Fine. So how would we go about doing this correctly with unique pointers? Because there is a way to do it. And it isn't that much more difficult, but it is a little bit of extra work. So I'm going to go check out our unique pointers branch. We have one for raw, shared, and unique, and you can see this all on GitHub if you want to check it out on your own at the time. And we're going to go back here. And here, we have some unique... We do have unique pointers. Yes, I switched over. We have unique pointers right here. And you'll note what we did. Make unique pointer of type food. And note, it returns a unique pointer of type food, and a vector holding these. And it also takes this in. So here, we actually can use new. That's my bad. That was a slip up. So we can make new bananas, new bread, new eggs, new pancakes. And from here, we're going to make a vector of type unique pointer, holds food, food vector. We're going to push back each one using move. And then we're going to call these functions, all with these moves right here. Now you'll note what I have here is I'm setting food vector equal to what the function returns each and every time. Why? Well, let's rather than ask the question, let's actually just modify it so that we don't do that. And then I'm going to ask again, why does this happen? So let's go back, let's go up. Let's go to bin. Let's run this. We only got the food is cooked 3 times, but if we look at our code, what we did is we check to see if it's prepared, then we prepare our food, then we check if it's prepared again. But what happened is that we only checked if it was prepared 3 times, right? So why did this happen? Does anybody know? Take a quick drink. No. Okay. So what we did when we use this std : move is, remember, when we push something into a function, we're copying it over to that function. So we copy the value of food vector, copy the pointer to food vector over to this function right here, check preparedness, and what it's going to do is it's going to do whatever it needs to do in this function, and then it goes out of scope. It leaves the parentheses and it's gone forever. The destructor is called. So let's actually make this a little bit more apparent. In fact, let's go to our banana class. I need to open banana. And we'll go to and cd source, and let's open banana. Bananas. And we'll go to our destructor. Let's make sure we have a destructor. We do have one. Let's just make sure I didn't initialize it to nothing. Bananas.h. So we have a virtual destructor. So let's make a destructor real quick. So bananas and tilde bananas. And we'll call cout and say destructor called. Let's see what happens. So we'll go back up a row, we'll go to builds, and we'll make it again. Bananas, what doesn't it like? Implicitly declared, oh I'm sorry, I do need to explicitly declare in the header. Tilde, bananas. Make. Let's go to bin, let's run this. It doesn't call the thing, it doesn't say that it's destroyed, because it's destroying the vector. So that was kind of a useless example. You know what? It was there. Anyway. So what happened was that we destroyed the vector. Because the vector of unique... Yes?
When the vector is destroyed, you call this destructor vector?
I didn't use a virtual destructor. That was my own fault for not setting this up enough. But what you're supposed to do when you do inheritance is that you use a virtual destructor. So that destructor then calls the following destructor and then destroys whatever it needs to. If I'd used a virtual destructor, it would have called that. Apparently I didn't do that though. That was a solid my B, but just know that it will happen if you do. Yes?
What were you doing with destructor?
So I added a line to our destructor. So when the object was destroyed, it would call this. However, I didn't make our base destructor virtual, and we're getting an issue now. Just to make sure, let's actually try and just do that real quick. And make sure that isn't my only error. So we're going to go to cd and include and subl food. And let's make this virtual. And that should do it. If it doesn't, then I made a mistake somewhere else, and that's my bad. bin, and there we go. So, moral of the story. What's happening is that the objects in our vector are getting destroyed, and so we can no longer go about using them because we have a vector of size 0. And in fact, to prove this, I can actually just check the size of the vector at each one of these functions. But yes?
Before you had foodvec assign the value of those three, return value of those three functions?
Yes.
What were you doing there?
So that's what I was explaining. So what happens is that when we pass these into these when we pass our vector of unique pointers into these functions, we're destroying everything inside this vector right here and pushing it into this function. And then when it goes out of scope in that function, it's gone. A little confusing. Does that make sense?
So foodvec is passed to this function, but there's something that happens inside of the function where it makes a memory leak? Is that what you're saying?
No, it doesn't make a memory leak. In fact, it does the exact opposite. If we have a function, make another function, and void, and this is going to take, no, it's not
I
going
know what scope is.
So, yes, I'm sure. Well, let me show real quick. So we have an int number, we're going to call a function. And then we're going to make another int in here. And this is going to return nothing. Actually, we can make this equal to 5. Not equal to f5, I'm sorry. And then we can add one to number. And we can then print out number if we want. And number. And what's going to happen is that we'll be printing out the number 5 instead of the number 6. So, wait, does that make sense?
Yes.
So, yes. So what happens is that we make this variable called number, and even though we have an equally named thing here, they're not the same variable. And that's exactly what's happening inside of here. We're making our vector of unique pointers here. We're adding things to it. And when we use std::move, what we're doing is we're ignoring this value here, we're destroying it, and we're passing it into this function. And this is like a declaration of its own. So this is equivalent to when we said int number inside that other function equal to 5. Whatever we do with it inside this function is not going to carry over when we go back, even though they're pointers. Okay?
And that's different from C.
That's different from C because if you pass a pointer into a function, if we just used a raw pointer,
Yep.
the value would be changed inside here. And the value is being changed, it's just we discard the unique pointers when we're done with them. Because they're unique pointers, and we can't have more than one pointer to an object. So to fix this, what we have to do, I'll bring this back. What we need to do is return our vector of unique pointers every time we're finishing. So then we can set our food vector equal to what it just was. Okay? Because what we've done, we destroy it using this std::move and copy it over to this function. It's more like cut and paste, I should say. Then what we're going to do is we're going to cut it and paste it back here. So every time you pass a unique pointer to a function, you need to make sure that you have a way of returning it to its original variable if you're not done with it. So let's actually run this and show that it works. Oh, did
And
not
why-
save.
Why does it go away like that? Is it because it's unique pointer that it's only...
Yes, because it's, no, well, we're using make. Sorry, we're using, doing two things at once. We're using std::move. And that moves everything from a variable over to what it's being called to in the function, or wherever it's being set, wherever the thing is being set.
Oh, so it's now in the scope of that.
It's now in the scope of this function rather than the scope of our main function.
Okay, and it will die with the function.
Yes.
Because now it belongs there.
Yes.
Okay.
And now we'll run it, and it does everything because we're setting it back equal to what it was before. Okay? It's a little convoluted there. Did I lose anyone? How many people did I lose? Everyone? Because of my mishap with destructors there? No? No questions? All right. Let's get to some more fun stuff. I wonder how many times I've shown this unique pointer slide now. All right. And multiple ways to instantiate. Now, let's move on. Let's move out of pointers for now. Talk about iterators for a second. We all know iterators. Iterators are kind of annoying. They're verbose. Look at that syntax right there. Ooh. Oh, man. All we want to do is just make a loop to go through our array, or a vector in this case, and then just process that data. And yet, what we have to do is we have to do std vector. We don't necessarily need this. Object of whatever type we're using. Maybe a pointer to it, maybe not. We're making an iterator of I, and we do list.begin. That's pretty dang verbose. There's lots of boilerplate code that goes into starting this loop. It can be a real pain to do it over and over again. Who wants to do that? Nick, you're fired. Programmers are lazy. This is why we program, so we can automate things we're doing. Why are we writing all this every single time? Shouldn't be. Right? This is where auto comes into play. So, what does auto do? C++ contains a beautiful abstraction called auto. And unless we're using a language with duck typing, like Python for example, C++ is one of the very few languages that has something that does this. And what it does is that the compiler decides what type the object is. What this means is that there's no overhead. So it doesn't figure out what the type is at runtime. When you compile the code, it figures out what it is. So you can sprinkle auto all throughout your code, and it's perfectly fine. Your program will not run any slower. Now, it cuts down on verbosity. Like we showed the iterator example, it makes it much easier to write. Look at this. Oh, look at that. I'm breathing in a sigh of relief. That's beautiful. All it is auto. Ready? So, let's go back. Let's actually just do this right now. Yes, question.
What is I now? Is it a list?
I is exactly what it was here. It's a vector, it's an iterator to the type of vector, to the vector of type object, where it begins, yes.
So once it gets the return value of list.begin, it'll make I that type?
Yes.
Something like that?
It can tell what type the list is. And in a fuller-fledged example, which we can actually show, we'll go back to our code, our terminal actually. Let's switch over to our, one more up, and just do a raw. And we'll go back to our example. And here, this is fuller fledged because you can see what type our vector is. And we can just go about replacing this. Let's run it. Look at that, it just works. Let's get rid of it here too. Why not? Who am I to say no? Auto everything. It just works. Auto is very handy. But your question brings up an interesting point. If you throw auto everywhere, what happens? Now it becomes difficult for the programmer to understand if it's something that's crazy. So, here, it's pretty obvious we're working with iterators, and we can tell what type it is. So we're just going to use it like a standard iterator, and then call our function, and whatever we need. But, this can get really out of hand if we go about using it, say, for return types. or for other types as well. We could actually, I don't know if we could do it with a void function, but if we had a return type and other functions and we put auto for all of them, the compiler wouldn't complain, but suddenly the programmer reading all of these wouldn't necessarily be able to tell what each function did. And that can be a real pain. I'm going to pop up an example of, so make sure, get out of here. Make sure you know when the right time is to use auto. Auto can be used everywhere, but you don't necessarily always want to use it everywhere. Only use it when typing out what you're working with becomes incredibly verbose. And let's go to our shared pointer. Let's pop this back up. And here we have an example of auto, just like what we just did, and it works exactly the same. Okay? That makes sense? Are there any questions about auto? Cool. Let's go back to here. I'll keep it going. But it gets even better. Why would you ever write a for loop if you don't have to? For loops can be disgusting. You have to write for thing. You're going to declare a variable. Maybe you're still using auto equals list dot begin and I doesn't equal list dot end and plus I. Oh my gosh, my hand's getting tired. This is terrible. It's disgusting. All because we just want to loop from the beginning to the end of our lists. In fact, most of the loops we write are just for looping from the beginning to the end of a list. Why would we not just make something that does that already? Well, the thing is, the fellows who made C++ said, this is silly, let's actually do that, and they did. So what happens is there's an easy peasy way to loop through everything. All we need to do is for said type I, and then we just do the list, and then we loop through. Just like that. Beautiful. But it gets better, and I kind of just did it right there. There's an auto for each as well. So you get to forget the type, and the compiler can handle it very easily on its own. For auto I colon list, and we just loop through. Beautiful. All right. So let's go to our last. Are there any questions so far about for each loops? Yes.
Would list be whatever like vector or something?
List would be, yes, if I showed a full example, list would be vector of type object or pointer to object, and then we just go through that. I'm starting to run low on time, so I don't want to jump straight to the example, but that's that. So we can bring up the final thing we're working with, references. References are strictly C++ compared to C. You will not find any references in C. If you ever work with Java, everything is references. You don't need to worry about that. It's Java class. So what is a reference? It is effectively pointers, but without the pointer syntax. But it's not a pointer. It's very important to understand that. It is not a pointer. What it really is it just another object right there? It is effectively the exact same thing as the object. So we make the pointer. What happens is that C++ says, this is a raw pointer by the way, we need so many bytes. I believe it's 8 for a pointer. Is that right? C fellows? 8? I don't know. We'll say 8 bytes for a pointer. And it makes the address. And I'll get it. It is? Okay, good. And it's going to make the address 0x123 4 or whatever we're going to use. And that's going to point to an object. Okay? This takes memory. We are making a pointer to this object. When we do a reference, what happens is that we're not making a pointer to an object, we're pretty much just making an alias to an object. It's pretty much just a new name for that object. So if I make an example here. But it's very different, but it's very similar. We're working with that exact object. We're not making a pointer to it. So this is denoted by a left-hand ampersand. Note, I didn't have to draw that one out, so it turned out beautiful. And what we can do with it is it can allow for massive performance gains. So, for example, that for loop we talked about before. Let's go back to it for a second. This right here, what we've done is we made a list, a for each loop, type I, to a list of whatever object type it's going to be. Just like what we're doing with functions, what we need to do is we need to copy that object to I every single time. Or we need to copy a pointer to that object I every single time. With a reference, what we can do is just make it so that it is that object. And it doesn't take any copying whatsoever, it just becomes it. So now we don't have any double things going on anymore. In fact, this also solves a problem that we had earlier. Let's go back to our unique pointer. Let's pop that open. And you'll note, here we have these beautiful examples of for each loops. Let's make that a little bigger real quick. What we've done, and there is another way to do this, but it's disgusting, so I'm not going to go into it. And this fills what we need to do. What we've done is we made type I, which is a unique pointer to this, but we've made a reference to it. We're not making a copy of a unique pointer anymore. Instead, it's just becoming that unique pointer. Then we can cook the food and return the items to cook. And we do it again down here. We're not making a second unique pointer to an object. That is that unique pointer. Okay? Did I lose anyone so far? Yes?
So instead of now using star I in the for loop, you get to use I. Is
Yes.
that one of the changes?
Well, that's one of the things. Yes, we're no longer making a pointer to it. We're now making it become that object. So we don't need to dereference it anymore because we're not using pointer to pointer. It's just reference to objects. It is the item in that list. And this is the easiest way to loop through a list of unique pointers. Yes?
It's not passed by reference.
That is passed by reference. It's literally passed by reference. It is a reference. Yes. You can sprinkle references everywhere, actually, not just here. Yes.
So, what does it look like in memory?
What does it look like in memory?
Yeah.
Memory does not really change. It's more or less like
Like what does the variable end up looking like? Does it hold the address?
it doesn't hold the address. It's like if you're using Zish, for example,
Yeah.
you get a lot of free aliases. Okay?
Yeah.
So you notice that when I was working with Git, I would do stuff like GCO for Git checkout or GST for Git status. I'm literally just running those commands. It just expands those to become the commands that they are. You can see all my aliases here. That's literally what the C++ compiler is doing. It's just saying this is another name for this thing that we're looking at. This is a reference to it. Okay? Takes no memory. Zero. That's why references are pretty cool. But they can also be kind of scary. Okay? When you use a reference in a function, you don't need to know it's actually being used. Because everything you do in that function does not need to have any unique syntax. So if I go into our example here, and this is a bad example because it uses unique pointers. Let's flip into, I'm actually going to compile it. If I just put a reference here, now I'm working with those actual objects. And if I change them, now I've got an issue. Because now I'm actually changing what's happening there. I'm no longer changing a copy of it. If you're expecting pass by value and you get pass by reference, that can have some absolutely awful intended side effects. So you need to be cognizant of whenever you go about using pass by reference. And it's most often used in loops or when you know exactly what's happening. It's also important to have strong docs along with your functions so that you know when you're using, like these, so you know when you're using references as well. All right? So make sure you're careful when you're using references and that as a programmer you understand when you are. It's easy to just throw references all over the place because they make things very fast and they also make it so that now you're modifying everything there, but it also makes it so that you can have unintended side effects where you accidentally modify something that you didn't want to. Okay? You may never know when you're working with them. And that's our issue. All right? And that's it. So there is your intro onto unique pointers, shared pointers, references, and modify. Are there any questions? Anything I didn't cover? Did I lose anyone when I was screwing around with the structures earlier? No? All right. You're free to go. Bless everyone. Operator overloading next week, and that's it.